want to talk to you a little bit about this because this is a concept in networking that you really probably should have somewhat of an idea as to what's going on and how it interacts with the greater IP world. Now, these particular examples that I'm going to be using, we're talking about something called IPv4. Okay, this is the traditional, 4-octet IP range, and so a typical, let's just say the default, right, for a lot of BirdDog devices, 192.168. Say it with me now, 100.100. You're going to find that IP address on a lot of BirdDog devices as the fallback IP address. And so if you know, if you've interacted with any of our devices in fallback, you know that that is the IP address. So we're going to be talking about IPv4. This is not really about IPv6. Some of these concepts translate, but not really. In IPv4, we have the ability to set IPs to certain ranges. And why you would want to do that is there's a greater conversation about how networks work together. Okay? So why would you want to break up a network? Why wouldn't we just have, a single switch and have like a bunch of devices on the network, right? And so we're just going to, create hundreds of devices, and just for demonstration's sake, I'm just going to make a whole bunch here. So we're just going to have a bunch of devices, and we're going to connect these all to this switch. Like, why not just make it all just one big flat, and other ones too, going off into greater directions. And we're going to do hundreds of devices, and they're just going to be, like, logically, why doesn't this just work? Why don't we just have a whole bunch of devices and they're all connected to the same switch, and we, just have hundreds and hundreds and hundreds? Well, manageability, really. And the first piece is it's really hard to manage a network that is this big and this unintelligent. And so just from a sake of making your life easy, you want to put some sort of level of intelligence into the network. But the other piece about this is each of these devices, if they're operating correctly, are broadcasting. And so, device, whatever number this is, device over here in the corner is going to say, hey, who is so-and-so? Well, if each of these devices is like .1, .2, .3, .4, and so on, right? And .6 wants to find out who number 1 is. It'll say, hey, who's number 1? Well, it's going to send out a broadcast. And that broadcast is going to go throughout the entire network, and every single device that's on this network is going to say, not me, except for this one. Well, if all of these devices are wanting to communicate with various devices on the network, they're going to be all sending out constant broadcasts all the time, wondering who is who, right? And so you're going to get these, who is broadcasts. And generally, they're only looking for one of the device on the network. And so if it needs to be this guy, that's great. This guy will say, oh, that's me. But all of these other devices are going to say, not me, not me, not me, not me, not me, not me. And they're all going to be basically flooding the network. In the meantime, these guys are also going to say, hey, who is, so-and-so, and messaging out, and they're also going to be looking for, like, let's say this guy is, .8 or something like that. Hey, where's .8? Well, this broadcast is going to go out, and this guy's going to say, hey, that's me. But then they're also going to have a, hey, not me, not me, not me, not me, not me, not me, and so on and so on. And so you get bottlenecking is what you get. You get this big, it's actually called packet flooding, where you get too many broadcast requests and people cannot process enough. And this poor little $40 switch from Best Buy is not going to be able to keep up with you. So what can we do about this? Can subnetting be a little bit more intelligent? And the answer, of course, is yes. We've logically thought this through. Oh, that's weird. When I run off the screen, it cancels the option. So yes, we can do this a whole lot better. So what we want to do is think about networking in subnets, and there are multiple variations of subnetting in general. We'll get into that a little bit and understand how that's done. But we want to break up our network into manageable bite sizes that we can do this. And so how this is done is typically with what we would traditionally know as a router. Okay, so we're going to put a router on this network, and we're going to then create multiple networks And in these networks, these are traditionally what we would do is we would put, come on now, we'd put another router here, and we'd connect it like this to a switch. I should use different symbols for different things to make this helpful, but anyway, switches, routers, and so on. And we do the same thing over here and over here. And we would connect all of these together. Okay, switch and switch. And we connect these all together. And then we have devices on each of these networks, right? So they're all connected like this, and same thing here. Now, what's really cool is that all of the devices that are connected to these switches, which are connected to these routers, will all have unique addresses. And that's what an IP address is, right? It's a unique address that is assigned only to one device on a network that is, that is hopefully being controlled by a router. And so we get unique addresses in each of these. So this might be, 10 dot, what is going on here? I hate this. So this might be 10.1, and this might be 10.2, and this might be 10.3. But then over here, this might be, 11.1 and 11.2 and 11.3. All right, so we've got multiple networks. And when a device broadcasts, it actually doesn't go past the router. Okay, the broadcast request doesn't go past the router. But in a computer world, if we need to send data from 10.3 over to 11.2, the broadcast would go out to the router, and the router would know that that information, that address is not on my network, and then would send it intelligently through the respective routers and onto the network that it is corresponding. And so it would get to 11.2 through a routing topography, not directly over, over the actual switch with all of the devices plugged in like I showed in the previous example. So if we are sending a request or information to 11.3, the routers would take over and intelligently route that information over there. So we're going, now, if 10.3 wants to talk to 10.1, over here, then it would send out a broadcast request and would just hit this smaller network, and the information would just travel this way. Okay? But if we're going to 11.2, it needs to then go through these routers and then onto this network and get to the destination through a little bit more advancement. Now, it's really cool because we can create endless amounts of networks in the world and make them all manageable, because we don't all have to be on the same network. As a matter of fact, we can break this down even more, and things can be a lot faster. The broadcast request, for example, if you just have a handful of devices on a network like this, obviously the broadcast requests don't cause flooding, and it keeps things a lot quieter. And we're learning things all over the place about how we do this in NDI. But this is the idea of how IP networks are set up. Now, when we want to start doing subnetting allows us to separate networks in another way, where we can, now, and you've seen subnets that look like this. I'm trying to keep my brain somewhat organized, but bear with me. So you've seen subnets like this, okay? And the question might be, why are they like this? Well, in the computer world, computers speak a different language than these numbers, right? They speak binary, which is ones and zeros. And basically, 1 is open and 0 is closed, to put it overly simplified. Well, binary is worked out in a way through 8, they're called 8 octets. So we're going to create like this, go down the middle. And we probably need to do one more here somewhere along the way. Let me correct that, because that's wildly inaccurate. So, all right. So we got 1, 2, 3, 4, 5, 6, 7, and 8, right? So in here, we have a numbering system. So this is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64, and this is 128. Now, subnets are a way to, this is, I should accurately hear, this is subnet masking. This is an important term. And we'll talk about NDI. We'll go right down to the NDI specifics here, but so that you understand. 255 is all of these numbers added together. All right, so it's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. It equals 255. But in binary, what that means is there are 8 little there are 8 what's the phrase? It just left me. 8 bits. There we go. There are 8 bits in each of these IP, in each of these octets. So we have 8 spots. And if the spot is taken, is consumed, then we have a 1 in that location. And so for 255, okay, we've got 8 spots. 255 means every single one is basically valid, or yes. And so that means we have a 1, 1, 1, 1, 1, 1, 1, 1. Okay? That is, in binary, the actual what the octet looks like in ones and zeros. Because each of these, let me change my color here, each of these is used. Okay? So we have we're using 128, we're using 64, we're using 32, we're using 16, we're using 8, we're using 4, 2, and 1 to get 255, which means that every single bit is a 1. So 255, 255, 255.0 in binary looks like this. Whoops, I'm using green. Sorry. Let's change that. Like this. Because 0 is obviously none of those bits are being used during this. When a computer gets an IP address, when it looks at the subnet mask, anything that is a 1 is considered a part of the subnet, is not a part of the addressing system that IPs used. And so when we say using a single subnet that is 22255, what we're saying is the way the computer is reading the network data should only be using the last octet to distinguish devices on the network. And so all the devices on the network, for example, all have the same first 3 octets, so 192.168.1. Those are all the same across the entire subnet, but the last digit is the identifier of the actual device. And so this front portion is the network identifier, and this back portion is the actual device identifier in this particular scenario. Now, we can make this a whole lot more complicated by starting to change numbers. But so that you understand how computers are reading this, 255, 255, 255.0, the binary looks like this. This is what the computer is seeing when it comes into the subnet mask. When it comes into the computer or it comes into the device, this is what it's expecting and how it differentiates between who is who on the network. Now, you can change this number to be something else. For example, you can change this third octet to be 224. So what do we have to add together to get 224? Well, we can do this in real time. Let me pull this up here. Oops. So we can do 128 plus 64 plus 32. That gives us 224. So instead of, let me try and get a smaller eraser here. So instead of all of these bits being used, okay, we're going to take the green off of these. I should have made this easier to do. We're using 128, 165, I'm sorry, 128, 64, and 32 to do this, which means that in binary, this looks like 255, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we're using the first three, 1, 2, 3, and then 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that means that the first two octets and these 3 bits are going to be the network identifier, and then the rest will be the device identifier. Okay, so we can increase the number of devices we have on our subnet by the way that our network is working by changing this to 224. Now this works really well with computers, especially if you have a bigger network or maybe you have a wireless network where you have guests coming and going all the time, and you need more than 254 logical addresses on your network. But it doesn't work great when you're trying to do network nodes. Okay, when you're trying to control devices inside of a network and these are nodes on the network, you need to standardize the way that you're doing network IP addressing, which is why you may have seen our network rules where we say, please use a 255, 255, 255, 255 addressing system. Basically, that means that this is the network identifier right here, right? This last one. This is the this is the device identifier. And the network identifier is going to be this number. The way that the NDI protocol seems to be written is in this configuration. Now, there are ways to create additional subnets within a router so that you can have certain floors of departments on certain subnets and that sort of thing. And NDI actually has it written into Access Manager to allow for that variation. But if you're sticking to the actual network topography that is assumed with NDI, and now we're going to kind of get into the NDI discussion. If I've glazed over some portion of the subnet that you are super confused about, please say so in the chat. But NDI is, in general, built on this idea that you're going to use a 22255 NDI network structure, which means that the first 3 portions of the IP address are going to be the same, and that the last digit is going to be the identifier of the device. Now this is kind of fundamentally worked into whether you're going to use DHCP or static. It doesn't really matter which protocol you're planning on using. This seems to be a fundamental part of the base structure of the NDI protocol. Now, to be fair, this may not be intentional. This may just be the way that they designed it all those years ago, and it just continues to operate on that assumption. So you may say, well, why do I have to only be restricted to 254 IP addresses? Well, you aren't necessarily. You don't. We can talk about making this more sophisticated, but if you're going to have 254 devices on your NDI network, we're probably not talking about TCP anyways. We're probably talking about multicast, which is a different animal in and of itself and does network addressing differently. And so if you're switching over to multicast because you've got 100 devices, well, some of this stuff is not really super relevant at that point because multicast operates at the network level and not on the device broadcast level. So we would always say, hey, if you want an out-of-the-box experience, we want you to use 22255, and the way that you think about that then is, okay, the first 24 bits in the IP range, okay, all of this, again, this is 22255. All of those are going to be the network identifier, and then that last set is going to be the actual, whoops, I did those colors backwards, really sorry. I'll do this. So that last set is going to be the device identifier on my network. And that way, let's try and be consistent here, Knudsen. So, and that way, we know that when we see an IP address that's set up this way, and we've set it up. So if I say 192.168.85, that is my NDI network. And so if I plug a computer into the network and I get issued an 85 address, I know I'm on the correct network for my NDI stuff. It's actually very convenient to troubleshoot and manage on the back end, because as production people being introduced to IP workflows, you're going to be managing the network in some fashion. And so let's make this simple for you. When you set up your custom IP range in your DHCP, make it unique. 192.168, pick a number between 1 and 200. 192.168.85. I know that is my range. And if I plug a device into a switch and I get an 85 address, I know I'm going to be able to see the NDI information on the network. That is the idea, at least, behind how to make this simple for you. Okay? Even the New Tech University stuff, which is a great course, by the way, taught by Kane Peterson, and it is worth the money to do if you're seriously getting into NDI. But even the New Tech course says, hey, look, if you want to do this simply, we recommend DHCP, and we recommend that you use a single subnet. And the single subnet looks like this. If you're talking to network people about this, like, hey, I'm not doing the network setup, and I need to be able to talk to my IT department about this. This is known as a slash or a WAC 24 network. Okay, a WAC 24 or WAC 24 network. Basically saying that it is a 22255, or it's written this way, where if you say, hey, I want my IP range to be 192.168.85, WAC 24, that's how you'd write it out. Hey, can you make me a VLAN that is this? You would write 192.168.85.1/24, and your network guys would know, okay, they want this to have a gateway of .1, and they want this to be a 22255 network. That's network admin talk. And they might question you, and they might say, why do you need 24? Like, can we make this can we give you a part of a network, or why is that required to be 24? Now, there are other combinations while we're talking about subnetting, for example, where you could do 255.255.255. What is it? Here. 190. Shoot, what is it? 128 plus 64 is a 192. That's what it is. So you could write it like this. What 192 is going to give you is it's going to give you less addresses. It's not going to give you 254 logical addresses. It's going to actually limit your addressing. So in the binary world, it's going to look like this. And what that does is actually limits you down to having only a certain amount of IP addresses in this specific range, but this will actually enable you to have multiple subnets. Okay, so when you write a subnet like this, what it does is it allows you to have a subnet, and you can break it up into, I believe it is 2 networks. I can't remember. I don't actually regularly do this. 2 or 3. What's the logical? We can find out. What is the logical network chunk? If we do. So if I just type that in here to the almighty Google. Yoink. Not HT. Chrome is trying to be too smart. Okay. Here we go. So when we are talking about subnet masks and we say 192, that is a 6-bit, right? Because we've got 6 bits here on the end. So if we go back to our devices, we've got 6 bits here, which is our identifier, which means that we can have 64 addresses. Okay, so that breaks our network up into, what is that, 4? 4 segments, 64 times 4. Yes, 64 times 4 is 254 or 256. So this would give us 4 subnets in this configuration. And you can even do, and this is known as a WAC 2.6, by the way. This is a WAC 2.6 network. So this is where if you wanted to do actual subnetting and you wanted to have multiple subnets across the same NDI range, instead of doing VLANs, you could do subnets, and you could say, I want a WAC 2.6 subnet, and this would give you 4 subnets to work with. And then you could logically separate them by floor or by department or by switch or by something like that. So when you plug into a portion of your network, you would get a specific subnet address, which then you could tell, oh, I'm on floor 3, or I'm in the finance department, or I'm in the NDI network or the Dante network, or break it up logically over subnets. It actually does make it quite manageable in terms of now you can separate things over subnets. The difference is that now you're going to need to use something like Access Manager to allow cross-subnet traffic, because NDI is going to want to stay in its own lane on its own subnet. And so if you were to do something like this, you would need to then tell Access Manager, hey, I've got cameras on 3rd floor and I'm on 1st floor, and I need to be able to see the 3rd floor cameras. But this goes outside of, this is not a VLAN. This is a subnet separation, and that actually allows you to have a more manageable side of things on the IP level, where you can see the IP address that gets issued on the DHCP and know, hey, okay, I'm plugging into the switch on a finance port, or I'm plugging in on the 3rd floor, or I'm plugging in on the NDI network. Depending on how you break it up, the subnet can actually allow you to separate the data that way instead. So if we were to then just say, well, what do we need to do for NDI? And why was NDI developed this way? Well, the why I can't really answer. I don't really know why specifically we went with a 22255 network, because I wasn't there when it was invented. But it does appear that things are in the SDK, and the SDK is the piece of programming that NDI gives to everyone to develop their products. This is basically what the go-to is. Doesn't mean that it is the only way to do it, but this is kind of the default. If you were to take something out of the box and plug it in, NDI kind of expects that you to be running over a WAC 2.4 network. This can be changed, but does it need to be changed? Probably not, because this will do enough until you get to the next level of sophistication. And so I would advocate, from a out-of-the-box experience, if you're doing unicast, this needs to be your go-to. We don't need to overcomplicate things. We don't need it to be for you to have a humongous network for no apparent reason, because if you're going to have a humongous network, you need to be talking about a more sophisticated design like multicast. One more thing I'll say about this. Some people say, well, I don't want to be limited to 254 IP addresses. Now, they say 256, but 2 of those addresses are reserved, and so you're going to only get 254 usable IP addresses on a 22255 network. But some guys will be like, well, I don't want to be limited, so I'm just going to do double 255. And what this will do is, remember what we were talking about earlier, this will mean that the identifier, the network identifier, is going to be this section, and the device identifier is going to be the back end. And we know in binary what this looks like, right? So we know that the first 2. Oh, I'm sorry. That's it. That's not correct. Sorry. Because each of these are representing bits. So in each of these octet, there's 8 bits. And so what's happening is the network is going to be on one side, and the device identifier is going to be this giant conglomerate. But there's a major problem, is that devices, and specifically network nodes, are not able to catalog and get literally get to all of these devices in the amount of time that it has to get across the wire. And so if we're doing a double 255 network, we're talking about 64,000 IP addresses. So when you go from a single 200, a single octet being the identifier, so a triple 255, we have 254 addresses. If you, and especially if you don't know what you're doing, if you just change it, instead of the network mask being triple 255, you go to double 255, these IP addresses is 64,000 IPs. Okay? And not IPS, that's Internet Service Provider. Ugh, I hate all these shorthand. 64,000 IP addresses. And you think, well, then I'll just never run out. The problem is that you won't be able to you actually, the devices themselves will not be able to navigate the network and communicate with those devices on the network. And so this is not a great idea. Doing a double 255 is not a great idea when we're talking about NDI networks. We need to be sticking to something that's manageable, not only for you, but also for the actual network nodes. The NDI SDK seems to be under some assumptions when it comes to networks. And the first is that your network is well aware of what it's doing. And that doesn't translate over to the Dante world. Because Dante actually has some things working behind the scenes that help it traffic the data. But Dante is also using very low amounts of bit rates, very low amounts of data when it's passing the audio channels. And so it's not requiring heavy loads of information to be passed quickly. It is purely just requiring that the low amounts of data get passed across the network, effectively and quickly. And so when we're talking about a few megs versus 100 or more megs, that's a lot more work to be processed. So with NDI, we need to be sure that we adhere to a specific set of networking rules just to make it make sense for the network nodes that are already on the network. So people get bent out of shape when we send them a list of network requirements that say, please set up your network this way. And then we get network admins that say, well, I know how to do networks, or I know I know what's best for my switches or my network. It's like, first of all, none of us have more than 5 years experience running NDI because it really hasn't been around that long. And hand on heart, we haven't done a very great job of telling you how to design a network for NDI. That works well with NDI. And so you've got all these guys that have been in the field since day one, and they genuinely have done trial and error over those years and have come up with their own bag of tricks that seems to work. But we really do recommend, and again, for the plug-and-play usability of the cameras, we really do recommend that you run it in DHCP, that you have a single subnet or a WAC 2.4 network. So this is triple 255, right? So we can say, let's see how we can write this. Okay, .0. So we have a DHCP network that's running a WAC 24 network. That's going to give us 254 IP addresses. And that's going to be sufficient for a TCP or a RUDP network, okay? That will give you what you need. But the actual network management that's going on behind the scenes here is pretty important, which is why we say a DHCP. Now, if you want to run in static, you can. And I have been accused, and rightly so, in the past of saying don't do static. Because I know the type of tickets that it generates. You can run this in static, and wow, that was, oh no, sorry. Clicked a notification. Okay. You can run this in static. And I wrote that poorly. He chose poorly. Oh my gosh. Stinking teams. It keeps taking up. Okay, let's just go down here. You can run your network in static. Absolutely. However, we do recommend that you're still running with a triple 255, so a WAC 2.4 network. which will give you 254 IP addresses. And I recommend that you this is a better way to do this. I recommend that you run a discovery server. This needs to be on a Windows or Linux machine. And this IP address of this computer, which will be in static, is going to be your default gateway. So when you are on a BirdDog device, let's just say it's a camera, like a P200, inside the static information, you're going to set the IP address. You're going to set the subnet mask at WAC24, okay, 22255, and then your default gateway is going to be your discovery server IP address. In addition, you're going to turn on discovery server on the P200, and you're going to set that IP address to the DS computer IP. That is how that should function. And then once you do this, you're going to hit restart video. And when you hit restart video, you're going to watch the discovery server, which will be running on the computer that you got it running on. You're going to watch discovery server, and you're going to make sure that that source gets added to DS. If you do that, that should make things work fairly consistently. What DS is doing, and this is a great understanding as to how this all works. What Discovery Server does is when you turn Discovery Server on your P200 or your camera or whatever, it stops the broadcast requests, it stops the bonjour broadcasts, and it sends the broadcast directly to the IP address that you've indicated. It sends a broadcast request to that IP. When that broadcast, gets to that IP address, it gets logged inside Discovery Server, and Discovery Server then keeps an active list of all NDI devices on your network. Now, the cool thing about this is that it stops the broadcast requests, which means that your NDI devices will stop broadcasting. It also means that when you open Studio Monitor and you're not connected to Discovery Server, you will not see those sources. So it's a cool little way of quieting the network, of securing the network a little bit. It's not the greatest way to secure the network, but it helps a little bit because people can't peer in on your live streams, on your cameras and that sort of thing. But it also makes sure that your static network has somebody that is listening actively on the network. And so when you say, well, I want to run static because then I won't lose the IP addresses, all good. But for NDI, you're then going to be required to have a computer that's running Discovery Server. And that is then the logical way of setting up your IP addresses for your network, and more specifically, what it is that we're talking about when we are doing subnet masks. And where is it here? It's this one. This one here. The 22255. That is this one. This first, in binary, it's this one right here. That is the one, the way that your computer is going to be reading your IP information across the network. And that keeps it simple and keeps it consistent across all NDI installations, first of all. But I do believe that this is the baseline for how the IP structure was built and is expected to run for an NDI installation. All right, I'm sure that was mighty confusing. I have no doubt that it probably was. I'm happy to take some questions if you have any, but hopefully that gives you some insight as to why it's important we do the subnet mask information correctly and why we keep it down to a 22255, a WAC24 network, why that's so vitally important.